In the previous two videos, we've looked at expanding functions that are a product of two or more functions, as well as a quotient of two functions. In this video, we're going to fall way back on a topic from college algebra called composition of functions, where you will see an outer function with an inner function combined. I will give you some tips on how to find the outer and inner functions and to follow this expansion. So again, we're going to let f of x and g of x be two differentiable functions. We're going to define the derivative with respect to x of f of g of x. In college algebra, this was written as fog, so you'll remember that kind of composition. In a collapsed notation, it's f of g of x. The expansion is f prime of g of x times g prime of x. Now, to put it in simpler terms, it's derivative of the outside, inside part left alone, and that's what f prime of g of x is. It's the derivative of the outer part with the inner part left alone times the derivative of the inner part. So let's walk through some examples. Let's let y be defined as 3x squared minus 4 quantity cubed. In a simpler function, this would be simply m cubed. But this is used to recognize the outer part. The outer part of this function is something cubed. Well, if you have something cubed and you take the derivative, it would be 3m squared. 3 something squared. This first part, f prime of g of x, is nothing more than taking the derivative of the outer part, which is 1 times 3. The inside left alone, that's why this g of x is identical. The inside part gets left alone. So it's 3 times this squared, and that's when you take off 1 from your power. This last part where you chain on the derivative of the inside, your interior part has a derivative of 6x. First and last, since all this is a product, you can multiply and get 18x times 3x squared minus 4 quantity squared. So it takes some getting used to. You have to look at it in terms of inner function and outer function. It helps if you recognize the outside part as something cubed. Something cubed. And then your outer derivative would be 3m squared. So it's 3m squared, but the original term stays the same, and then you take its derivative and chain it to the end. Let's look at a second example. 3 times the cube root of 7x plus 4. Remember that we've been writing radicals as fraction exponents or rational exponents. A cube root has a power of 1/3 when translated. So this is 3 times 7x plus 4 to the 1/3 power. That's equivalent to a cube root. All right, so our comparison is 3m to the 1/3. 3m to the 1/3. That's the outer part. So taking the derivative and applying chain rule, 3 times a third, that's 1. Inside part left alone, 7x plus 4 left alone. When you take 1 away from your power, 1/3 minus 1 is negative 2/3. Now chain the derivative of the interior part to the end. That derivative is 7, so 1 times 7 is 7, times 7x plus 4 to the negative 2/3 power. It is totally appropriate to stop here, so I made a note. You can stop here. If you want to make that exponent positive, you transfer it to the denominator, so 7 over, and then that will be cube root of 7x plus 4 quantity squared. This part is optional. In our third example, we have g of x defined as 1 minus 4x to the fourth. We can compare that to y equals m to the fourth. It's just something to the fourth power. The derivative of the outside will be 4 something cubed. 4 something cubed. That something is your interior part left alone. So it's 4 times 1 minus 4x cubed times the derivative of the interior, which is negative 4, and that gives us negative 16 times 1 minus 4x quantity cubed. The next example, function f of x defined as 6x cubed minus 12x all to the 4/3 power. We can compare that to m to the 4/3. The derivative of this outer part will be 4/3 m subtract 1, that'll be 1/3. 4/3 m to the 1/3. Again, the interior part comes down, that stays the same, and then on the end we chain this derivative, 18x squared minus 12. 4/3 times these two numbers, 4/3 times 18 is 24, that gives us 24x squared. 4/3 times negative 12, that's negative 16. 6x cubed minus 12x to the 1/3 power, you can translate that to cube root of 6x cubed minus 12x. Again, that's optional. This is totally fine. If you wanted to do a little more reduction, then you can go forward. Just be careful. Our last example, we're going to define g of x as the square root of 2 minus 9x. Again, a radical you can write with a rational exponent. Specifically, a square root is a power of 1/2. So our function can be rewritten as 2 minus 9x quantity to the 1/2 power. What would we compare this to? That's right, you would compare that to y equals m to the 1/2. M is all that interior part, our exterior is a power of 1/2. If you were to take the derivative, you would get 1/2 m to the negative 1/2 when you subtracted 1 from your power. Use this in the main problem. So this outer derivative is going to be 1/2 2 minus 9x to the negative 1/2. Again, leave the interior alone. And on the very end, you chain the derivative of the interior to the end. So that derivative is negative 9. That gives us negative 9/2 times 2 minus 9x to the power of negative 1/2. This step is totally fine to stop on. If you want that exponent to be positive, carry it to the denominator alongside this 2, and then change it back to a square root radical, giving you negative 9 over 2 square root 9 minus x. Square root of 2 minus 9x. I think I said it backwards. Again, this looks cleaner. This is okay. Reach out if you need any help with your homework. I can be reached by email or phone, or swing by the office. I'll be more than happy to help you out, or just ask in class.